Hi everyone. In this video, I'll walk you through a Python-based tool which I have developed for automated cricket batting analysis. The system uses computer vision to break down a batsman's technique from a single video. It basically tags the key points and shows us, according to our calculation, whether he did it right or wrong. Um, It automatically tracks the player's pose, calculates key biomechanical metrics in real time, segments the shot into distinct phases like downswing and impact, and generates a comprehensive performance report, which can be accessible to anyone who doesn't know how to code, or it can be represented easily. Alright, let's look into the code. The entire project is structured into logical modules for easy access. As you can see, if you want to change anything, it's very easy. So the main pipeline is our named as cricket shot analyzer. Its analyze video method is the main entry point. It handles all video IO using OpenCV, reading the input file frame by frame and writing the annotated output video. It initializes all the other helper modules and manage the main processing loop. As you can see, this is the whole code. So next we'll look into pose estimator class where we calculate the pose. It's a pose estimator module. This class is a wrapper for Google Media Pipe pose library. It's configured with a confidence level from our config file. According to the config file, the output will be changed. Its job is simple but crucial. It will return 33 detected 3D landmarks of a person in it. I have also included a helper method to draw the skeleton on the frame for visualization. Now we'll see the biomechanic analysis module. This is where the core analysis happens. This module takes the raw pose landmarks and translates them into meaningful biomechanical metrics. For example, calculate angle. Function takes three joined coordinates, say shoulder, elbow, and wrist, and uses vector math with dot product to compute the angles between them. We have similar functions to calculate the spine lean relative to the vertical axis and the front foot direction. This accurate analysis I took from external sources. A key metric is normalized horizontal distance between the head and the front knee, which is crucial for assessing balance and head position. This module is responsible for creating the visual feedback on the output video. It takes the calculated metrics and uses OpenCV's putText function to draw them into the frame. It also provides instant feedback by color coding the values like green, blue. This is also where the current FPS and short phases are displayed. This is the evaluation module. After the video has been processed, the shot evaluator class takes the complete history of metrics for the entire shot. The calculate score function is the heart of it. For each metric, it calculates the average value and compares it against the ideal range defined in our config file. The score from 1 to 10 is based on how much the player's average deviates from the ideal reference. It also calculates smoothness score to reward consistency. Finally, it aggregates these overall score and assigns the skill grade into beginner, advanced. According to our config file and tweaking these values, these can be changed. These are just placeholder values for now. We need relevant data accordingly to perfect this or train the model to get these accurate values so that it can be used in a wide range of videos. Let's zoom into the biomechanical analyzer so that we'll see how it calculates the angles. So here you can see the calculate angle function is great example. To find the elbow angle, we need the coordinates of the shoulder, elbow, and wrist. We treat the elbow as origin and create two vectors, one pointing to the shoulder vector A and one pointing to the wrist vector B. The angle theta between them can be found using the dot product formula, and it is done by NumPy. Handing missing or handing missing or low visibility joints is critical for making system robust. Its MediaPipe by its own provides a visibility score for each landmark. Every single metric calculations like the calculated angle begins by checking if any of the required inputs are none. If so, it immediately returns none for that metric on the screen. This prevents the system from crashing and more importantly, stops it from polluting our analysis with guessed or inaccurate data. We simply skip the metric for the specified frame, ensuring that our final average is based on only high confidence detections. So this is the entire code, and this is the config file. We can change it. I made this configuration manager because it can be easily changed and edited so that we can use it whenever we want. This detect confidence, tracking confidence, visibility threshold, max missed frames, FPS target. These values we can change, and the model or the program will work accordingly. So let's run the code. So I have already set up a Python 3.114 environment with all the necessary libraries. I choose 3.11 because the MediaPipe libraries has not been updated in the latest Python version. So I tracked back to the oldest one, which old but the newer versions which MediaPipe works efficiently. I'll run it again because here you can see your FPS score. The other scores, if it's good, it will show us as green, the faces. I change the text a little bit small because I'll run it again. I'll change the text a little bit small because everything will get clustered here. So, yeah. So, yeah. So, then the outputs will be analysis log. Here we can see what happens, what is the FPS, what are the frames processed. This is one of the thing that the program outputs. Then the output file will have the annotated video, which is the same with the better quality. The other one was real-time video, which was processing. We'll have an evaluation JSON with the scores, which we can use to train any other model or uh, identify what this model is lacking. Then we will have the report file. This is a generated HTML file so that we can assess what or how the person is playing. Then we'll have the graphs in the separate folder. So what are the limitations for this? The main limitation is 2D analysis. It's based on 2D image coordinates. This is susceptible to errors like from camera perspective and can't fully capture 3D moments. Since we are the second main problem is since we don't have or uh, a wide range of data set to train and we don't know the actual edge conditions or actual key values that should be the thresholds so that it would work perfectly fine. In this case, this video it works decent enough, but the phases, and as you can, as you prefer, there are multiple phases. The change in phases will be dependent. There will be multiple edge conditions. That all we can identify through training only. The basic backtracking, the current bat detection is simple placeholder using color segmentation, which is not very robust. And the phase logic, as I said before, it's very easy. It's based on wrist velocity, but it's not like, it's not 100% accurate. The next steps will be moving to 3D, a robust wall and backtracking, which would highly improve the phase tracking, data-driven benchmarks, and UI development. So that's a complete tour of the cricket batting analyst tool. It demonstrates the practical pipeline from video input and actionable feedback using modern computer vision libraries. Thank you.